Hello, we are proud to present Human Preference Next Best View Selection for 3D Gaussian Splatting. Our motivation is to use 3D Gaussian Splatting, which is a novel view synthesis method that takes a bunch of Gaussians and renders it into photorealistic and geometrically precise scenes. Our motivation to use 3D.js is if we want to understand scenes and learn objects, we often use a camera on a robot or phone. And we want to do this efficiently in few views and autonomously, which brings up the question of how can we view informatively next in a scene for the most informative view? Prior next best view methods are heuristic in nature and very unintuitive. So we propose to leverage preference learning to guide the next best view to efficiently reconstruct a scene. Our method will answer the question, how can we get a human where a human would say, I trust myself to view better than these methods to view next in a scene? And our key insight is to learn a preference model based on human preferences on labeled pairwise data.
So our contributions are to generate this human preference dataset, train a model on the dataset, and then use it for next best view selection. For the preference model, our recipe is to collect a bunch of unlabeled images generated by a Gaussian splat, then have a human label these pairs of images to identify the worst looking one, and then train a model that is ideally a ResNet along with a Bradley-Terry model to then output the same uncertain image. So here's a visual representation of how we collect the data and generate the pairs and then pass it on to a human for labeling. Then the human looks at the pair and then inputs a 1 for whether 1 or 0 for whether image 1 or image 2 is the more uncertain or noisy looking image. Here's an example UI for how a human would label the images. And once we collect this human preference dataset, we then train the model, which, like I mentioned, was a ResNet along with a Bradley-Terry output layer, to then provide a preference image, which would then be used for the candidate next view. And here's some images of how the model performs on an evaluation set.
Now we talk about 3D Gaussian splatting and how does it integrate the framework. So to start, we talk about how 3D Gaussian splatting works, which is from the radiance field equation. So the idea here is that if you represent a human eye as a camera, given a viewing direction and position, x, y, z, and theta and phi, what do we see? If you shoot out rays, each ray we see a different color. So 3D Gaussian splatting uses this rendering equation on the bottom right and takes a bunch of Gaussians in 3D with color, position, scale, and rotation and smashes it into a 2D surface. And this should match the camera images we took. We can also leverage geometric cues. This is Gaussian splatting over time. It starts as very few Gaussians and slowly becomes into thousands of Gaussians that faithfully represent the art. Next best view. In next best view, each view is very critical to the reconstruction quality. Prior works, such as Fisher-RF from ECCV 24, use heuristics, even though they claim to be theoretically motivated. We actually improve upon this baseline. For preference learning for view selection, there's two approaches. Here's the first one. For every n steps in training of a Gaussian splat, we select a new view. We run the preference model F over many pairs of candidate views, and then take the Condorcet winner over the views and select the winner. However, this is horribly inefficient as it's O of n squared. It's not actually quantitative in nature, and we want something more efficient in O of n time. That leads us to the best method, which is running the preference model F over the training views and collecting the features. Then we run the model over candidate views, also collect the candidate features, and select the features that have the highest median distance between the training view features. We then use the preference features as a metric, which we find intuitively encodes human preference and gives us strong next best views. Our overall pipeline consists of collecting data, training the scene model, and then training the Gaussian splat and getting views with our preference model. Our experiment setup consists of using the MIPNERF 360 dataset, which is considered standard for next best view selection. We use data collection, in which we train poor splats and query many camera views to get rendered images. We do our labeling and training in Pandas and PyTorch, and we run our view selection on 3 challenging indoor scenes. Here are some scenes that we run on. Our baselines are random, Fisher-RF, for a scene ablation using approach 1 of our method, and our full method. On the kitchen scene, we find that our method beats Fisher-RF approach one, as well as random views. Here's a qualitative result that shows less artifacts and visually a more pleasing image to the human eye. On the room example, our method further destroys Fisher RF by a large margin. We can see again that the novel views match up with how a human would want to see views. Finally, on our counter result, we actually match state of the art, but we find again that some novel view renderings show that our method shows nice and human kind of intuitive views. Our analysis is that novel view synthesis is improved with using common sense from a human. And even though we rely on quality human data, we plan to scale up into one model for future work. Finally, operating in feature space is most suitable. We conclude by saying human preference is a very promising direction for next best view selection, as this is the first work in the field that uses human preference to quantify new views in any kind of radiance field. Our future work will have one model distilling human preference for Gaussian splatting. Thank you for your time.